for this questions, we're trying to figure out how many ways we can tile 2 times n board. So based on the instruction, there are 2 different types of dominoes, one with 2 squares and one with 3 squares. And for the 2 squares, we can do it horizontally or vertically. And we can also rotate the Tromino tile. So for this problem, the goal is to return the number of ways to tile and 2 times a board. And since the answer might be large, we have to modulate it with the 10 power of 9 plus 7. So we first look at the example. So when the number n equals 3, we're trying to figure out the ways to tile a 2 times 3 boards. And based on this example, there are 5 different ways. And for the example 2, if we're trying to tile a 2 times 1 board, there are only one way, which we can only put vertical dominoes here. So for this problem, we are using the method dynamic programming here. So we can break this problem into some similar subproblem. So here's the PDF I drawn. DPI here means the total ways that we can tile a board with for 2 times I board. So the DP is the array we can save the ways for the specific index. So how can we tile 2 times I board? There are 4 different situations. The first one is we can add vertical dominoes at the end of the 2 times I minus 1 board, which will work. And the second situation is we can add 2 horizontal dominoes at the end of the I minus 2 board, which will also work. And the last 2 situation is we can add Trominos at the end of board, which we have 1 extra square outside sticking out of it. Because this kind of board doesn't match the original board we have, so we use another list called DPA to save it. So we define this kind of board, we call it DPA, and the way we can tile this is BP at the index of I minus 1, which means the way we can tile this. Based on this observation, we can think that the way we can tile the 2 times I board is the way we can tile the I minus 1 board plus the way we can tile I minus 2 board and the way we can tile the 1 extra sticking out board and the symmetric one, like the sticking out square is at the bottom of the board. This is the first formula we got. And the second question is how can we define the way the special board that there's 1 extra square that's sticking out. So yeah, we can solve this problem by break this into some subproblem. So the first one is we can use I minus 2 board and then add a Trominos at the end of the board. And the second situation is we can use the symmetric one and add horizontal dominoes at the top of it, which will also make this board. Based on this observation, we can have a formula DPA I. If we're trying to tile this board, it will equals the way we can tile a I minus 2 board or a special board, which is I minus 1. And the situation is exactly the same with the symmetric one. So when the square is at the bottom, the 2 situation is exactly the same. Only when the second one, we have to change the situation into the square at the top of the board. So since this two situation is symmetric, we can assume that the way we can tile these board are exactly the same. For the first formula we got here, it can be written as dPAi equals dPi minus 2, and we replace the dPb into dPa minus 1. Okay, so we are going to do some quick math here. So the first formula here we got as written in here. I said previously, the dPb is symmetric, which equals to the dPa. So combine these into the same one. So we got the first formula here. And then this is the situation when dPi. So when dP equals I minus 1, the situation will be exactly the same. And we're just replacing the I into I minus 1, which we did here. And this will be the second formula. And then for the second formula here, we can try to rewrite it into dPa I minus 1 minus dPa I minus 2 equals dPi minus 3. Yeah, just a quick math here. So by subtracting these two formula here we got here, and then replace the dPa into using the third formula here, we can get our final formula dPi equals 2 dPi minus 1 plus dPi minus 3. And this is the exact formula we want here. Okay, so back to the code. First, we want to create a DP list where we know the base case. When DP equals, when the board is 1, we got only one ways to tile it. And when the board is 2, we have two different ways to tile it, which is two vertical dominoes or two horizontal dominoes. So there's 2 when n equals 2. And when n equals 3, the example shows us that there's 5 output here. And then the rest of the list will show 0 as we haven't calculated. Yeah, so here's a length of n where the index shows the ways we can tile the exact n input. Okay, so we'll iterate through this DP list by using our formula we got. So exact formula we got here. Yeah. And remember, since the answer might be large, we have to do a module here. 10 power of 9 plus 7. Okay. Add a semicolon here. Okay, dPi equals dPi minus 1 times 2 plus dPi minus 3. Yeah, and I think this will work. Since our list is 0 index, the way we can tile 2 times n board is at the minus 1 index. And okay, so it passed the test. And for the time complexity here, since we only iterate through the list 1 and the n is the length of the list, the time complexity of this is O of n. And for the space complexity, we create extra list, which called dp. So the length of the list is also n. So the space complexity of this algorithm is O of n.